Okay. Good morning, everybody here in Argentina. Welcome to the third day in this beautiful conference on fluids. So it's a great pleasure for me to have here John Bush, which is he's now the head of the Applied Mathematics Lab at the MIT. And after his BS in physics at the University of Toronto, he went on to Harvard. That's right, for his PhD in geophysics, then to Cambridge University at the MTP. John, you joined the MIT in '98. And I think you start your research in geophysics, and then he was interested in surface tension phenomena and their applications in biology. And for a few years, he's been working on the quantum hydrodynamic analogy in fluid mechanics. So he's going to tell us about it. Thanks again, John, for being here. And so please, whenever you're ready.
Very good. Thank you. Thank you for the introduction, Irene. I'm happy to be back in Argentina, if only virtually. I've been to Argentina for a couple of FLUIDOS meetings. There was one in Tunuyán and one in Tandil, as I recall. Can you see my screen?
Yes, that's good. Okay. Perfect.
Very good. And I apologize, I've not been able to attend more of the meeting, but I'm in the throes of both. I had a grant to do today, and I've been teaching as well, but I'll try and tune in a little more in the coming days. So I'd like to share the work that I've been doing for about the last 10 years, actually, on these hydrodynamic quantum analogs. And I should start by thanking those responsible. So Yves Couder, who unfortunately passed away 2 years ago, got this whole project started. And I've, since beginning on it, I've had a number of graduate students who have gone on to great things, collaborators, postdocs, and instructors at MIT who I've worked with on this project. And I should also thank the National Science Foundation for their unwavering support. Okay, so when we think of quantum mechanics, we think of a theory that describes the statistics of microscopic particles, while it doesn't describe their trajectories. So the totality of their description of a free particle is it has an associated energy, h bar omega, and an associated momentum, h bar k. So this is basically associating a particle with a wave, but as any undergraduate will naturally ask, where is the particle? And why does it move? And these are questions that they have failed to address. And those who sort of insist that their description is complete have prompted all sorts of difficulties which have been lingering for almost a century. So we have the proliferation of quantum interpretations, many worlds, and so forth, an abundance of paradoxes, quantum paradoxes in public language. And so any attempt to describe the particle trajectories, these are called hidden variable theories, which makes them sound somewhat mysterious, but they're not in the least bit mysterious. They're simply the theory that would describe how these microscopic particles move. And these all, it turns out, so all the hidden variable theories posited to date involve a particle entering with a background wave. And so in terms of the history, so the first such attempt before the very notion of hidden variable theories was around was proposed in the 1920s by Louis de Broglie. So he proposed a particle moves in resonance with a guiding wave. So a particle has an internal vibration, excites a wave, and then moves in response to it. This was his original physical picture, from which actually Klein-Gordon equation, Schrodinger's equation, those derived to describe his guiding wave. Subsequently, they've been adopted to describe the statistics of the system. Now, sometime later, David Bohm basically inverted, as we'll see, the Schrodinger's equation in order to get a dynamics for particles. And he had his physical picture was much simpler than that of de Broglie. It involved only a single wave, this wave being the wave function of standard quantum mechanics. There's also some attempts. So Nelson proposed stochastic dynamics and can basically explain or understand the motion of particles as being a sort of a structured random walk. And the most developed hidden variable theory is that of De La Peña and Cheto. So they basically also, it's a pilot wave theory in which particles interact with the electromagnetic quantum vacuum. Okay, so that's the sort of background. Again, all hidden variables, all attempts to describe particle trajectories involve particle interacting with its own wave field. Okay, and so so what does this have to do with fluid dynamics? Well, in 2005, Yves, Couder, and Emmanuel discovered a hydrodynamic pilot wave system, again, which involves the particle moving in resonance with its guiding wave. So this is really, it's bears a strong similarity to this sort of double solution pilot wave dynamics proposed by Louis de Broglie in the 1920s, and lo and behold, exhibit several features of quantum systems that were thought to be exclusive to the microscopic realm. So it's only logical that one asks the following question. So what are the key dynamical features responsible for the quantum-like behavior? We have now answered that question. What are the potential and limitations of this hydrodynamic system as a quantum analog? This is a question that we're still exploring. So we're basically continuing to extend its range as a quantum analog and see what its limitations are. And can it guide us towards a rational theory for quantum dynamics, that is to say, the motion of microscopic particles? Okay, so the system is familiar to many. If you take a vibrating bath and with a vibrational amplitude prescribed by, so the amplitude times the frequency squared defines a vibrational acceleration. And when this exceeds a critical value, which is around 4 times g, you excite these standing Faraday waves. So this is something one can see if you just put your cup on a, say, a motor or something which is vibrating, you'll see these Faraday waves excited. So at the Faraday threshold, these will be excited. All of the experiments to be described today operate below the Faraday threshold, but they have a drop in them, and the drop excites the wave. So in Couder's system, they basically said, okay, let's put a drop on the surface. You can just create one with a toothpick, and again, vibrate the bath below the threshold so that there would be no wave in the absence of the drop. Turns out, so these drops are on the scale of 1 millimeter. They can be supported on the surface by virtue of the sustenance of the lubrication layer between the drop and the bath during impact. Okay. And so we have a millimetric drop bouncing on a vibrating bath, about 50 hertz, and we're using silicon oils between 20 and 50 times the viscosity of water. Okay, and so the remarkable thing, so it's been known since the 70s that you can levitate drops by vibration. What Yves discovered is that these drops are sometimes unstable. So at a critical vibrational amplitude, these drops become unstable and start moving in response to their own wave field. Here we see this drop slowly moving from left to right, and it's moving because it's landing on the slope of its wave field. So of course it's creating, as it bounces, it creates a symmetric wave field, but it becomes unstable at a certain amplitude, and so then it will basically land on the side, and you get this periodic so-called walking state. And so the key thing to realize is this instability from a bouncer to a walker happens after, so these Faraday waves are subharmonic. That is to say, they have twice the period, half the frequency of the driving of the bath. And so you need to have a period doubling in the bouncing of the drop. So once you've got a period doubling, so when it first bounces, it bounces with the frequency of the driving. But then as you increase the driving, the period of the bouncing increases until it matches that of the most unstable Faraday wave. Then you have a resonance between the drop and the wave, and then it goes unstable to this walking state. And so the key feature here is, in order to calculate the propulsive wave force on the drop, you need to calculate its slope. And its slope is, of course, in order to calculate the slope, you have to integrate backwards in time to take into account the impacts of all previous impacts along its path. Okay, and so so in order to get that force, you have to integrate backwards in time along the path of the particle. So this defines the system as non-Markovian. That is to say, the drop dynamics depends on its history. Okay, and so that's the whole key. So we call this feature memory. This is Couder's nomenclature. The system has this memory built into it by virtue, and the memory is basically stored on the wave field. And it's by virtue of this memory, this temporally non-local dynamics, that all of the quantum features arise. Okay, so this, you can see the memory arising in the trajectory equation. So we have mass times acceleration of the drop. This is a drag, which depends on the drag induced during impact and also the flight through the air. The interesting term is this wave force. So it's proportional to the gradient of fluid depth. And one can calculate that fluid depth by summing up all of the waveforms generated by successive impacts. So it's basically, we have a discrete sum over, it basically generates a Bessel function with some spatiotemporal damping. And the magnitude of the spatiotemporal damping is prescribed by this memory parameter. So this is literally, that's the time scale of decay of waves generated, so associated with viscosity of the wave during impact, the Faraday period, and this is the vibrational acceleration gamma. So as the vibrational acceleration approaches gamma f, the Faraday threshold, then the memory blows up, and you have to integrate over a very long time to calculate, to adequately account for the past, the system's past. Okay, and so there are other parameters that we have to do so forth, but this is the key thing. So you see, this memory parameter prescribes the rate of decay of the guiding. Instead of describing the full dynamics, let's just strobe it and describe the horizontal dynamics. So if you grab one frame per bounce cycle, then you just see the particle being propelled along by its guiding wave. And notice it's dressed in this quasi-monochromatic wave field, whose wavelength is the Faraday wavelength. So that's the most unstable mode of the cavity. And this is a very important physical picture also when we start thinking about what's happening in quantum mechanics. Basically, in de Broglie's physical picture was the same, but with the, instead of the Faraday wavelength, you have the de Broglie wavelength. Okay. So, so we have the stroboscopic model now, and so again, with the full model, we had that rather unappealing infinite sum. But if we imagine description in this frame where the particle is simply gliding along the surface, we average out the vertical dynamics to describe the horizontal dynamics, and we can consider the particle as a continuous source of waves, and so that infinite sum then becomes an integral. So we then have an integral differential equation, which is amenable to analysis. We can assess the stability of various dynamic states, bouncing, walking, orbital states, and more complicated things, all of which we've looked at. So here's an example. We've looked at the stability of lattices of bouncing drops, so pairs, we see triplets, and basically you get these static bound states which are quantized by virtue of the wave field. They want to sit in the nodes of their neighboring wave. Okay, and so here we have free rings on the left and the bottom. On the right, we have ring bound within a channel, and as you increase the vibrational acceleration, these rings of drops will go unstable to a number of different forms, which we can rationalize with this theory. So here we see the sort of ratcheting top left. Here you see, at the bottom we see the circular ring go into a pentagon and a square, and here with a confined ring you see solitary waves propagating around the ring. So it's a very rich hydrodynamic system which can keep one busy for life. I am most interested in its implications for quantum mechanics. Okay, and so we also have dynamic bound states. So drops, this is shown very early by Couder, drops can lock into orbit with one another, or they can execute these promenading modes where they walk in the same direction side by side. We've looked at the stability of those. But again, I'm most interested in this system as a quantum analog. So this got started with Couder's experiments in 2005. He looked at drops passing through. So no sooner had he discovered them than he said, oh, well, this reminiscent of de Broglie's mechanics. Let's see what it does with the slit experiment. So here we see a walking droplet going towards a slit. So this slit is basically, there's a submerged barrier across which it cannot cross, but it can pass between the slit. So as it passes through in any given instance, it's deflected by an angle alpha. And over on the right, we have the distribution of alphas. So they mostly go down the middle, and then there are these two wings on the side. You see this diffraction pattern coming out, and it's because of the action of the pilot wave with the slit geometry. And of course, this is much ballyhooed in quantum mechanics as being a phenomenon which is impossible to understand. But in these experiments and subsequent ones, it has been shown how coherent wave-like statistics emerge from chaotic pilot wave dynamics. Okay, so here's the double slit experiment. You also get a sort of robust diffraction pattern. And so, these were done very early on by Yves. And so before perhaps they realized how sensitive the system is to drop vibrational acceleration. So they didn't, in this very early paper, they didn't even report those things. And it turns out the system is exquisitely sensitive to these parameters to learn to control them. So I had a wonderful grad student, Dan Harris, who built a very precise rig and drop generator. So we can really bring precision to the required to the problem. So in particular, Yves got all of this data from a single drop. So basically one experiment running continuously. And if you're gonna, given that it depends on drop size, you really need to, unless you're gonna do all your experiments with a single drop, you need to have reproducible drops. So that's what we did. So we went back and revisited this problem. We found something similar in certain parameter regimes. Of course, it was impossible to identify what parameter regime they were in, but nevertheless, in a sort of broad range of parameters that we considered, one gets something very similar to what they have. You have a central peak and then two wings. You have this diffraction pattern, and there's in fact been even more refined experiments done recently in Denmark, and their results are consistent with ours and consistent with Yves. So there is a robust diffraction pattern. And in terms of the double slit, so the important thing here, this is the great mystery in quantum mechanics, the diffraction pattern changes. So if you have a second slit here, so despite the fact that the drops, that the particles don't pass through that slit, its very presence changes the behavior. Okay, and so here we look at the diffraction pattern going through a single slit, identical slit, but we have a second slit there, and you can see that the system pulls the influence of the second slit, again, by virtue of the fact that the particle is dressed by this wave. This wave feels both slits. And so there's this sort of, it appears to be a non-local influence of the second slit on the particle path, okay? And there was some people will object saying, oh, well, it's not the Fraunhofer diffraction pattern. And there's very little reason, in my view, why the diffraction pattern should be exactly the same. You do have diffraction here by virtue of the particle being dressed by a wave. In the sort of standard textbook pattern to which they compare these diffraction patterns, the one that one should use, because in that particular limit, the slit 1,000 times the de Broglie wavelength. Here it's order 1. So this should be like a sort of a near field. We should be comparing it to a near field rather than a far field approximation of the quantum problem. And we'll see. So one expects there to be different pilot, of course, there's going to be a different pilot wave in quantum mechanics and different boundary conditions. So we don't know what those are. But nevertheless, you see these sort of how chaotic dynamics can lead to apparently non-local effects. Okay, and so this is another example of a non-locality here with a walker. So this is a walker approaching a submerged pillar. And these are actually Schlieren experiments. So we measure the full free surface so you can see the drop sweeping around. And we were just looking at scattering, thinking, oh, it's going to scatter. How do we describe that? And it turns out it locks onto this logarithmic spiral. And so which is rather odd. And so you can ask the question, so we know that the reason it's being deflected from a straight line, walkers always go in a straight line unless they encounter some force. or a wave perturbation. The only reason this is being deflected from a straight line is by virtue of the interaction between the pillar and its guiding wave. Okay, and so it's basically distorting its guiding wave in such a way that the particle follows a logarithmic spiral, which is quite remarkable. We weren't expecting that. And so you can then play the game and say, okay, let's deny that there's a pilot wave. Let's just assume that there's a force being applied at the presence of the pillar, right? So what force would be necessary to get to this trajectory? It turns out that it's a lift force. So it's proportional to the velocity of the walking droplet times its angular velocity around the post. And if we exploit this analogy between the Coriolis force acting on a mass m in a uniformly rotating frame and the Lorentz force acting on a charge q in a uniform magnetic field, you can see that this looks like the path is what you would expect if there was a charge moving in response to its own magnetic field. All right, so you consider then the charge moving along its path as being a current. You compute the magnetic field associated with that current, and then look at the Lorentz force acting on the particle. Okay, and so in any case, regardless, so it's very strange. It sort of looks like hydrodynamic self-induction, which is a peculiarity which I would like to better understand. But most importantly, you see that this wave-mediated force is giving rise to something that looks non-local. So it looks like action at a distance. It looks like, you can describe this, again, if you deny that there's a pilot wave, it looks like this pillar is applying a force at a distance on this drop. But in fact, in reality, of course, we know that it's wave-mediated, so it's not non-local. Okay, so another example of scattering we looked at is a particle. So these are so-called Friedel oscillations from quantum mechanics. So if you have C of electrons on a metal surface, they basically drift around, and if you have an impurity, they will scatter off it, and you can these concentric rings of waves, and these have the de Broglie wavelength. And to solve this, they just solve Schrodinger's equation, the scattering potential, and there's no notion of trajectories or anything like this. They just, again, you solve this with Schrodinger equation, and you're satisfied that you get the right answer. But there's no notion of trajectory. So we can do, we look at a walker interacting with a submerged pillar, and this is now drawn in along an Archimedean spiral. And then as it exits, it executes these inline oscillations. And so these are experiments, and we color code the trajectory according to speed. And so we see that as the drop exits these inline oscillations. And so in the fullness of time, you'll see that there's a correlation between speed and radial position. And this ultimately gives rise to a statistical signature, which looks very much like that in Friedel oscillations, right? So these are the speed oscillations, which you can see those translate to a probability distribution, which looks very much like that in Friedel oscillations. And of course, we can rationalize these on the basis of the particle dynamics. In particular, they're inline oscillations with the wavelength of the guide wave, which are responsible. So we can, the weakest possible conclusion you can make is that Friedel-like oscillations are not inconsistent with the notion of particle trajectories. Okay, so another of the early analogs was started by Couder. So they looked at a walker in a rotating frame. So now you have a vibrating bath also rotating. So if you have a particle moving at uniform speed v in a rotating frame, you expect it to lock onto an inertial orbit where you have a balance between the inertial outwards force and the inwards Coriolis force. So you expect the radius to go as the speed of the particle divided by the rotation rate. And so as the rotation rate increases, you see the orbital radius decreasing. And so that's what happens in the low memory limit in the Walker system. But at high memory, as you imagine from looking at this figure here, the particle starts feeling its own wake. So it starts moving on a corrugated potential of its own, and it's only stable at certain radii. And these stable radii are quantized Faraday wavelength. So it's basically stable in the troughs of this wave field. Okay, so if you plot then at high memory radius versus omega, you see this quantization emerging. So this was pointed out by Emmanuel Faure and Yves Couder in their early work, and we went back and revisited the problem. They also identified this very nice analogy, again, which we mentioned, between the Coriolis force and the Lorentz force, on the basis of which you can identify these quantized inertial orbits as, I think they're actually called Landau levels, okay, in quantum mechanics. Again, and this is true in all of the analogs, the Faraday wavelength plays the role of the de Broglie wavelength. Okay, so we went back and we revisited this system both experimentally and theoretically. So theoretically, we can just take our trajectory equation, throw in a Coriolis force, and we can look for orbital solutions. That is to say, motion with fixed radius or velocity. And you do, when you do so, you get if you express the balance of the two components of the force balance, you get a system of equations in radius and frequency that one can solve numerically. And so these are the solutions. This is the radius of the orbit versus rotation rate. So as in the mid-memory limit, you see that the solution branch blue has stable and unstable branches, unstable being indicated in red. And these are our experiments. And you can see that the theory does a very good job of rationalizing the experiments, and and so you can actually see that the quantization emerges because basically these orbital solutions lose their stability. And at high memory, one also has this sort of wobbling state. So this is basically when the most unstable eigenvalue has an imaginary component. So now as they go unstable, they wobble and then they fly off to infinity. And it turns out that you can, where the linear theory says they're unstable, you can actually get nonlinear effects which stabilize. But in any case, it's very robust quantization of the orbits, owing to the, again, sculpting of the interface by the. Okay, and so what happens at high memory? So this was not considered by Yves' group. So we basically to see what happens when these orbits go unstable. And so here's a circular orbit. We increase the memory a little bit. Again, that means increasing the vibrational acceleration. Then this goes unstable to this chaotic trajectory. And this chaotic trajectory, it's not completely random. You can see it's sort of jumping from circular orbit to circular orbit. So it's basically bouncing between these unstable, weakly unstable quantized orbits, right? So if you plot the orbital radius as a function of time, you see these toes, which is indicating a preference for certain states. And so you get these sort of multimodal quantum-like statistics. So these are, you can think of as the sort of peaks of the wave function corresponding to different quantity state. And again, you see here how coherent wave-like statistics can emerge from chaotic pilot wave dynamics. Okay, and another interesting feature of this examination was that we saw that the solution curves at high memory actually touched down on the vertical axis. So what is this vertical axis? It's the omega axis, so the rotation rate. So that means that you have the possibility of drop zipping around in its own wave field, even in the absence of a Coriolis force, which is normally confining force. But if the wave amplitude is large enough, then the wave force can actually balance the outwards centripetal force. And so you can have these, what we refer to as hydrodynamic spin states. And if you have one of these spin states, then as you increase the rotation rate, you get a splitting of these solutions, which is analogous to Zeeman splitting in quantum mechanics. Okay, and so it turns out these are unstable in the lab. So here's a lab trajectory. We try and get it onto one of these orbits, and it just drifts off. But you don't have to stretch your imagination too much to imagine a physical system in which a particle can be confined to move with angular momentum by its own wave field. Okay, and so we're going to come back to that, to the spin states. And the other sort of old classic was the Couder's group's examination of the Walker motion in the presence of a central spring force. So the drop wants to walk at uniform speed, but it's confined by the simple harmonic potential, and so it basically loops back. And what they discovered was that you get this double quantization of orbits. So you get this sort of family of orbits. So they're quantized in mean radius of the orbit, which is effectively the energy, applied potential, and mean angular momentum. So along this LZ equals 0 axis, you get the lemniscates, and along this line here, you have the circular orbits. So this is basically as the radius, and as the radius gets bigger, you get these more complex orbits. But they're basically, you have this emergent double quantity coming again from the sculpting of the free surface by the moving particle. And again, as in the rotating case, there we just had a single quantization in orbital radius, and you saw the chaotic regime characterized by flipping between these unstable periodic orbits. The same thing happens here. Basically, you get into when you get into a chaotic regime, it'll bounce between some number of these unstable orbits, and as a result, you get quantum-like. Not doing this in the this is the problem that I first looked at. So this is having been away from modern physics for some time. This is the only problem I could remember how to solve, which was a particle in a box. So this is, but when I went back and, so when I started getting interested in this problem, I went back and was reading my old quantum textbooks. And, but I discovered that they've actually done the experiments now. So this is, again, particle in a box. The box is circular, so it's a Corral. But these are electrons zipping along on the surface of metal, and they're confined by this Corral, which you can see has a diameter of 75 angstroms. And this wavelength that you see here is the de Broglie wavelength. So what they do is they have a scanning electron microscope, and which allows them to measure the voltage on near the surface, which is a proxy for the probability of presence of the electrons. Okay, so they can basically calculate, they're basically measuring the wave function, which is rather nice. And so you can see how it emerges, and then you can also see how good their theory is, so how they actually match the theory. But in any case, so there's a circular Corral, there's a stadium-shaped Corral, and I thought, let's see if this works for walking droplets. So here we have a drop, which is a millimeter in size, walking in a Corral, which is several centimeters. And this is why our experiments are as good as they are, is because Dan Harris, this is what he cut his teeth on in order to get this to work, to really work on the refinement of his experiment, and he did a marvelous job. So again, so the trajectory here is color-coded according to speed. It's very complex. You think nothing's going to happen, but sure, in the fullness of time, there's a correlation between position and speed, and so you get a PDF which looks for all the world like what they see in the quantum system. So you see, once again, coherent wave-like statistics emerging from chaotic pilot wave dynamics. Okay, and so the physical picture that comes out of this really is that there are three time scales. There's the time scale of particle vibration, here the bouncing, which is around, again, the frequency is 50 hertz. Then you have this this sort of convective time scale, so how long it takes this drop to cross the domain, which is several seconds. And then you have the time scale of statistical convergence. And this, miraculously, is around an hour, right? So you can actually, all of these three time scales are all accessible within the lab, which is what makes this system so special. You know, if you consider the difference in scales, you know, going from angstroms to centimeters, you might think that this time scale of statistical convergence, for example, could be 10 years, but it's an hour. So one can actually do these experiments. And we went back, looked at the elliptical Corral. It's a very robust result. So you again get these bands of high and low speed, which give rise to the statistical signature. We show that they have basically control which statistical mode arises using topography, so to do something analogous to the quantum mirage. And the reason I wanted to mention this later study of Corrals is we discovered something interesting, which is that, so if you look at the wave at any given instant, it's a mess, right? So top left, the instantaneous wave is basically set on the drop. But then if you do a time average of that wave field, you get the thing in the middle. And that thing in the middle looks very much the particle histogram. And both of these are basically a superposition of two modes, okay? So, but the fact that the average wave and the particle histogram are so similar is quite interesting. And so subsequently, Matt Dury proved this. He says, okay, so if we can actually predict if we know the PDF, so if we know the statistics and we know the wave field of a bouncer, we can predict the mean wave field in the cavity. Okay, and this is, you can express it as the convolution of the wave field of a stationary bouncer. So that's the wave field you would get if the drop bounced in place forever. If you convolve that with the histogram, this U of Y, then you get the mean wave field. Okay, and so this is kind of useful because, you know, in some sense, the mean wave field is an interesting object because in some mean sense, that is the topography that the drop sees. So that's the sort of background pilot wave potential. And we'll see that this links very closely to Bohmian mechanics. Okay, so if you have so this is best illustrated, this notion of the mean pilot wave field. If you have a walker moving along a straight line, so we just do this numerically, time is advancing in this direction, but the particle is just moving left to right, and this is the red dots are the particle path, and the blue curves are its associated wave field. So at sort of moderate memory, you can see the wave field sloshes around and follows the particle. And at any given instant, so the mean wave field is indicated here in black. The instantaneous wave field is different from the mean. But at very high memory, the instantaneous wave field converges to the mean. Okay, and so basically the particle is then exploring its mean pilot wave potential. Okay, and it's a funny form because this mean pilot wave is prescribed by the statistics of the system. So again, it's non-local in the quantum sense. Okay, so we've seen now there are basically three paradigms for macroscopic quantum behavior. So they depend on the key thing, resonance between the drop and the wave. Okay, because that is the quasi-monochromatic wave field, which imposes resonance. And so we have this sort of picture of a drop navigating this non-local potential that is its pilot wave. So, for example, the pilot wave. So in the orbital pilot wave dynamics, we see that the orbits emerge by virtue of the imposition, the dynamic constraint imposed on the droplet by its guiding wave. And then when it becomes chaotic, you get intermittent switching between weakly unstable periodic orbits. And then we also saw in the Friedel oscillations, these inline oscillations, I think these are also important in the Corral, give rise to a statistical signature with the guiding wavelength. And then we'll see in some numerical simulations, and one can also certain lab regimes, an effective random walk. So the drops are basically moving at some speed and they reverse direction with a characteristic length given by the pilot wave field. And this is evocative of Nelson's stochastic dynamics, it turns out. So it really touches on all of the prior model hidden variable theories, which involve particles interacting with waves. I think it's interesting that it has connected to these sort of heretical models of quantum dynamics. And so now we have this growing list of this growing grocery list of hydrodynamic quantum analogs. And so every time I give this talk, I update this. We have some new things with super radiant tunneling and emission. And it goes on, and it's not just saying, oh, now we've done that. You actually understand these. You understand how to understand these systems from a classical perspective when we have the hydrodynamic analog. Okay, and so, but there's some things which are more difficult, some things which perhaps we won't be able to do. And it's clear what the limitations of the hydrodynamic system are, in particular, the viscous damping of the wave. Okay, so the very fact all of these systems emerge at the high memory limit indicate that this wave field, this lingering is responsible for the quantum-like wave field, sort of quantum-like behavior. And also we've seen that there's certain cases where the drop inertia can dominate the wave force. We really want to go to small inertia limit. So for example, the spins are stable or unstable because of part inertia. So we really want to go to small inertia, high memory limit. Okay, so what we can do now is we can say, okay, let's soften the focus a little bit. We know that electrons are not silicon drops. but we think that there's some common dynamics. And so let's retain the key features of the Walker system, in particular memory, resonance, and this quasi-monochromatic wave field, and go beyond the hydrodynamic system. So we want to sort of explore this generalized pilot wave framework with a view to connecting and informing quantum pilot wave theory. So here's a parametric generalization. So we just have three terms: the inertia, drag, and the wave force. And so we have two dimensionless groups, which prescribes the relative magnitudes of the forces. So this is basically the dimensionless inertia, kappa naught, and this gamma prescribes the memory of the system. So basically how long-lived the waves are. So this is 0 at the walking threshold and 1 at the Faraday threshold. So this just goes between 0 and 1. Kappa naught can take any value. So again, that says how important inertia is. And in the lab, it's strongly constrained to lie because these drops, walking drops, only exist in a tiny corner of parameter space. This is constrained to lie between 0.6 and 0.8 and 1.6. But what happens if it's 10 to the 16? What happens if it's 10 to the minus 14? What quantum features can we get? Then? When are these hydrodynamic spin states stable? When is the walking state unstable to inline oscillation? So we can now just look at this generalized pilot wave framework and map out the behavior of the system as a function of these two dimensionless parameters. So in particular, we find that spin states are stable in the small inertia high memory limit, okay? And so in that limit, so again, this is sort of where you are in the lab, but in this generalized framework, we can go to this limit where the spin states are stable. So again, the particles are then trapped within their own wave field, okay? So this is the spin region up here. We can zoom in, and there are these wobbling and precessing spin states as well. But by and large, most of the parameter regime, you have these inline oscillations. So if you perturb a system, the drop, overdamped oscillations means it just goes back to its free walking speed. These underdamped means they oscillate back and forth. And then you have this regime up at the very high memory limit where the thing is basically moving on the sort of random walk with diffusivity prescribed by the product of the mean speed and the Faraday wavelength. Okay, and so this is basically, you see that by exploring this generalized framework, you get more rich dynamics including spin, and so you can imagine further generalization. So this was just, a parametric generalization. You can look at it for alternative waveforms, different forms of damping, and we can also extend pilot wave. So we can start we're looking now at pilot wave dynamics in 3D. So the physical picture there is that a particle is a pulsating source of spherically symmetric waves. And when perturbed, it will go unstable and start moving. And sure enough, such is the case. And so now we've actually found 3D spin states, actually translating spin states. They sort of follow helical paths. And then you could imagine introducing a stochastic background field, which I would prefer to avoid, but it might be necessary. And again, this really allows us to connect with the quantum pilot wave theories and their modern extensions. So let's go there now in the time remaining. So the Schrodinger equation, here we have it. You can transform it into a hydrodynamic form. I was very happy when I saw this. This is the so-called Madelung transformation. So it's just a polar transformation of the wave function, but it turns Schrodinger equation into a pair of equations which are quite familiar to fluid mechanicians. In particular, so rho here is the probability density, S is the action, and U is the quantum velocity of probability. Okay, and so you have this, when you do this transformation, H bar, to begin with, you get I out of the equation. Second of all, H bar is confined to a single term, which is a so-called quantum potential. And that quantum potential, if you identify rho with the fluid depth in a shallow layer, then this is a curvature term. So it's basically acting to flatten out gradients in rho, which is what surface tension does, of course, to the depth in a water layer. So you can see H bar sort of playing a role similar to surface tension in fluid mechanics. And so what Bohm was trying to, this is basically his attempt to reinstate trajectories into quantum mechanics. He said, okay, well, let's say that the particle velocity is equal to this quantum velocity of probability. And if you do that, then you get the following trajectory equation, and you have it's non-local by virtue of the fact that it involves this quantum, but you can basically understand it as the particle moving in response to both quantum and classical potentials. And this is non-local by virtue of this potential. And it has other difficulties which were raised, and it motivated him to appeal to a sub-quantum realm. So now he threw in this stochastic forcing, which was we would now say from the quantum vacuum. Okay, but so two problems. One is it's non-local by virtue of Q, and again, why is it non-local? Q involves the wave function. So what you do is you solve Schrödinger's equation, you wave function, then you compute Q, and then you have the particle moving in response. So it's the particle moving in response to a potential which is derived from its statistical behavior. Hopefully that will sound familiar on the basis of what I just said about the bouncing droplets. Okay, and so Bohmian mechanics, if we compare Bohmian mechanics and Walker, so again, the de Broglie wavelength plays the role of the Faraday wavelength. Our dynamics is, of course, completely local. His is non-local and has ad hoc stochastic forcing. But if we identify the totality of these of the non-local potential and stochastic forcing with the wave forcing in our system, then we can see how one might make Bohmian mechanics local. Okay, so in particular, if we decompose our local wave forcing with a mean term, so this is again the mean pilot wave potential, which we've seen is non-local, and this perturbation field, then we can draw the following analogy. So what's worth keeping in mind is that they identified this mean pilot wave potential, this non-local wave potential from Schrödinger's equation, but you should really think, in my view, you should think of Bohmian mechanics as a mean dynamics. And there's probably, my feeling is, as de Broglie suggested, there's a second wave which is centered on the particle. But we can see how this sort of non-locality appearing in Bohmian mechanics might likewise, we might make a similar misinference if we were describing only the mean dynamics. And the main problem with Bohmian mechanics is there's no mechanism for wave generation. Again, you have this quantum potential imposed on the system by the quantum potential, which you get from the Schrödinger's equation. Okay, and in ours, the particle is generating its wave. So we have a source of wave generation. Okay, so
I'm sorry, John. We have just a few minutes because we have 15 minutes.
Okay, let me wrap up here.
Yeah. Okay.
Yeah. So the other sort of point of comparison is de Broglie's mechanics, where he said the particle is a source of waves. There's this oscillation at the Compton frequency. And so his mechanics looks very much like ours. He imagined a particle having internal oscillation, generating a pilot wave, and then giving rise to the statistical wave. So there are two waves. There's a real guiding wave and the statistical wave. Okay, so you can then draw a map between our system and his system. Okay, and so we can see some of the shortcomings in these quantum pilot wave systems. And so we had actually motivated an attempt to complete de Broglie's mechanics, so by embracing this notion of the particle of the source of its own wave field. And so we've done some simulations there, and that's really, these are sort of the frontiers which we're developing. Of course, it has to be consistent with relativity as well as quantum mechanics, but we're getting there's some very hopeful results. So just to conclude, we have this sort of vehicle for exploring the boundaries between classical and quantum mechanics. It certainly extended the range of classical mechanics to include quantum features. And we can see how quantum non-locality could be misinferred from a pilot wave dynamics, right? So these are all systems which I've mentioned in which there's apparent non-locality, but we can rationalize this non-locality in terms of the underlying dynamics. And we've seen that this system is strongly reminiscent of de Broglie's pilot wave theory. It suggests some of the shortcomings of the quantum pilot wave theories, and it's sort of motivating now. It's not just our group, but others are trying to develop models of quantum dynamics inspired and informed by this hydrodynamic system. So graphically, you used to, prior to this venture, there was classical mechanics, there was quantum mechanics. Now we have pilot wave hydrodynamics making inroads into quantum mechanics through hydrodynamic quantum analogs. We have this generalized pilot wave framework, which gives us a broader class of pilot wave systems to explore. And now we have this, what we call hydrodynamic quantum field theory. This is the attempts to complete a model of quantum dynamics with hydrodynamically informed systems. So that's it. Sorry for running over. I was going to fill a full hour, but there we have it. So right, and I'll just leave it at that, and welcome any questions that you might have.
Thank you very much, John, for this very interesting and informative presentation that led me to remember concepts of quantum mechanics. That's very, very nice. We are open for questions, but I want to ask you. Remembering some concepts and thinking on your conclusion and your framework, I was thinking in your walking droplet analog, if it is possible to describe something like a wave function with the phase and modulus I'm thinking on Schrödinger equation.
Mm-hmm.
Do you think that it's possible with this framework to?
Right. So we're actually doing some work right now, because it's clear that, so for example, in the Corral experiment, the statistical waveform we get is a solution. So basically it's the wave modes of the cavity. So if you have a statistically steady state, then the system so then the steady Schrödinger equation basically just becomes Helmholtz equation. So you're just looking at the modes of the cavity. So that's true in both the hydrodynamic system and the quantum Corral. So the steady Schrödinger equation is basically the same. And so we're looking now at relaxation to the steady state. And that should allow us to get the analog of the time-dependent Schrödinger equation. And we're actually using some stuff with machine learning now with Nathan Kutz, which is very interesting. So looking at trying to infer what the PDE is for describing the statistics from this pilot wave model. And we're seeing then how, for example, impaired measurement can come into it. So if we impose, say, uncertainty relations, we can think about how that is going to affect our inferences.
Okay. Hans, who is, let me know with that. Who is, I saw a hand. Where is?
Javier.
Okay. Hello, John. Hello.
Hi.
Hello, John. Nice to see. Nice to hear your blowing mind talk. Really, I mean, it's really kept me so interested in this new field that you have been attacking this last year. So I'm very happy to see your results, to see your research, your success in this field. So I was thinking a lot about while I was watching this. Nice talk. It looks like quantum mechanics concepts were already in the nature, I mean, at hand for the man before in the classical mechanics. So, because the most interesting thing that you have done here in this work, I think, is just put the quantum mechanics concepts that we all thought that they were only in the micro world. Right. Inaccessible to the naked eye, but you put it in hands in the lab, as you said, and it's possible to do experiments macrometric. So in the scale of centimeters of millimeters and time scale of an hour or so. So that's very very striking for me. So do you think there are some other non-hydrodynamical dynamical systems in mechanics or other fields of physics that can embrace these concepts of quantum mechanics? This is you are just dominating, mastering this this way of doing walkers, which is not very easy, I think. I saw the experimental setup, and it looks very sensitive machine there that you setup that you have there. But there are, I mean, if you thought of some other the physical system, macroscopic physical system that can embrace or include this quantum mechanics ideas or concepts.
Yeah, it's a good question, and a number of people have been thinking a lot about this. I, of course, love the bouncing drop system because, as you know, I'm a surface tension person. So I said, okay, I'm on this. And also the sort of links between H-bar and surface tension, the mathematical links is very strong. And so it's kind of, one has that, you know, if no one would ever tell me what H-bar was in quantum mechanics. So if I can think of it as a sort of a surface tension, I'm quite happy. But back to your question, so people have looked at, you know, can you get walkers, for example, on an elastic? So can you have a solid bouncing ball on an elastic substrate? So that's theoretically possible. I know someone is in another hydrodynamic setting looking at acoustically forced bubbles, because you can imagine if a bubble, acoustically force a bubble, the key is that it responds primarily to its own wave field. I mean, that's the secret to the bouncing drop, right?
Yeah,
it's responding only to its own wave field. And so that's the sort of trick. He's been trying to do this with bubbles, but right now they've found only a sort of chaotic regime where the bubble floats around randomly. It would be nice to get a sort of self-propelling state, and that hasn't been achieved yet. But I think there are others. I mean, there are various features of quantum mechanics which come up in pendulums and so forth. But in terms of this system has gone pretty far in terms of pushing the envelope and developing new analogs. And I wanted to say, you know, one other comment. I hurried it a little over the end. I mean, my view is that, you know, because of the comments, critical comments that I've heard over the last decade, one is saying, well, these quantum paradoxes have been around for 150 years, or sorry, for almost a century, right? So since the 1930s. What makes you think that they're going to be resolved? And I remind them that the fluid mechanical paradox, the D'Alembert's paradox, was 1750 to 1900. So that was 150 years. That took and basically at that time, the schism between experimentalists and theorists, which I see in modern physics today. And it was only when, you know, the resolution of the viscous boundary layer, Prandtl, around 1900, then modern fluid dynamics was born. Then we actually got rid of all of the paradoxes. There are other paradoxes like itinerant on data. So you have Stokes paradox and various, and these basically are rooted in the fact that there was there's a dynamics on an unresolved scale. And that's my strong feeling about quantum mechanics now, is that there's a dynamics on the Compton scale, as de Broglie suggested, which is unresolved. And when we resolve that, all of the quantum paradoxes will vanish.
Oh, okay. So there is still a lot to do in this field, and we have time. We have time.
Exactly. Still.
Nobody can complain. I mean, everything takes a lot of time. Okay. Thank you very much, John.
No, but then I think also, like, the encouraging thing is that, you know, it's a progressive approach, right? So one day we just understand this, then we understand this. As we get new analogs, we understand more and more. So, you know, for me, it defines clearly. It allows you to draw the line between what you cannot understand about quantum mechanics from a classical perspective. And importantly, it's a progressive approach. The line is moving, and it's moving in the direction of understanding more and more.
Okay. Thank you.
So we have Juan Gomba. Juan, could you ask John?
Okay. Well, thank you for the talk and the nice videos. It was very, very interesting. I would like to make a short question. I would like to to know if you have tried to reproduce some entanglement of particle states. For example,
Yes.
I don't know.
Yes.
Yes.
So yeah.
Okay.
So we're doing exactly that now, and our conclusion is you can. Well, we're refining things, but in different systems, we've sort of achieved super radiance, which is a kind of step towards entanglement. But we're looking at particle correlation. So, for example, just imagine a 1D Corral. So you have particles confined to wells, but these wells are communicating through a mutual wave field,
Yes.
and you're looking at correlations between them. And so Andre Nashpin has been doing a great deal of work on this. And what's becoming clear is, I think we will be able to violate Bell's inequality. And you can violate it by virtue of the wave field. So you basically have correlations, which are very mysterious if you don't know what the pilot wave is doing. But if you can see what the pilot wave is doing, it's no longer a mystery, right? And so the idea is, in entanglement, you start with two particles together, you move them outside the light cone, they say, right? And then they find that they're correlated.
Yes.
What is the light cone if a system has memory? So the notion here is that the two particles start together, they have memory of their initial arrangement, and synchronization. And the idea is they get synchronized by virtue of this pilot wave dynamics on the Compton scale. So if they're identical particles, they have the same frequency, so talk to other. Then you separate them. And the notion of light cone goes out the window when you're talking about systems with memory. So the idea is they have memory of their initial conditions or are correlated. So that, I think, I would predict, I can't say with certainty, but I would predict that we will violate Bell's inequality with the bouncing drops, and then people will say, oh, but there's a wave. There's no wave in quantum mechanics. And of course, our inference would be, well, there is a wave in quantum mechanics. You just don't know what it is.
Those results are close to be published?
Yes.
Oh.
Yeah. We're
I'm
working
going
on
to be
that.
very happy to see that.
Yeah, it's exciting. And then, it's sort of consistent. So these people, so Ana Maria Chetos is marvelous physicist in Mexico, and she has the same view of me on the subject. She goes, Bell's inequality has no bearing on pilot wave systems, on systems in which particles can interact through a field. And if you read, I mean, I did my senior thesis on Bell's inequality. The premise, he says, consider two particles moving freely, right? That's what he. And I say, well, these particles aren't moving freely if they're interacting through a common wave field. So in my view, stop reading there, right? Don't worry what he derived. Don't worry to what extent his inequalities were violated in quantum mechanically, because if there is a field, then it's irrelevant. So,
okay, thank you.
Thank you. It's a very good question, though. That's the holy grail in quantum mechanics, right? So I actually met Alain Aspect, who did the marvelous entanglement experiments in quantum mechanics, and he goes, "Oh, very interesting, but I don't think you'll ever do entanglement." So, this is the way it's gone for the last 10 years. Say, "Oh, that's good, but you'll never do this." So we'll see how it goes.
Yeah. Any other question? I have just a little one. Thinking on your work at droplets. I think there is no a dependence on the liquids. I think that you use silicon oil, but if you put something less viscous, the idea is not having a coalescence or something like that. Because I was thinking about if it is possible to have the same thing with a solid ball, for example, a solid sphere.
We tried to get the solid ball to walk with little success. So to begin with, in terms of fluids, you can actually do it with water. The problem is the water becomes contaminated. So if you get surfactant, if you get a piece of dust hits the surface, and then when the drop walks over it will coalesce. So surfactants are sort of notoriously ineffective on silicon oils, which is why we use. In terms of the solid sphere, one should be able to do it in principle, but we were using so the key thing is the maintenance of the air layer between the drop and bath. And so drops and interfaces are, of course, smooth on a molecular level. And if you have some roughness on the scale of the 100 nanometer lubrication layer, then you'll prompt coalescence. So especially, so for example, if you have a hydrophobic sphere, it'll have some rough elements, and those roughness elements will generally penetrate the air, then prompt wetting. So the nice thing about the drops is they're very smooth, and moreover they deform, right? So as they hit the surface, they deform a little bit, which means you increase the lubrication layer and the force which sustains them.
Okay. Thank you very much. So, any other question? I cannot see. So, thanks again, John, for this very nice lecture. And I hope next FLUIDOS to see you here in
It will be live. That's right.
Yeah. Yeah. Okay.
Back to Kundan.
Yeah. Okay. Very soon. Thank you very much.
Thank you. I'll be hanging around for a while. So.
Yeah. Thank you.